Okay, so in our three-dimensional model, Rn is R3, but has dimension 3. Your row space, assuming the matrix reduces in the way we think it will have dimension 3, so your null space will have dimension 0. We map that over here, and it's a similar picture to the one we've had, into Rm. Now M is 6, this is dimension 6. And our column space has to have the same dimension as the row space of A. Column space of A is same dimension as the row space of A, and the column space of A is the row space of A transpose. So this has dimension 3. And this having dimension 6 means we also have a three-dimensional null space that's orthogonal to this. Now you can imagine 3 dimensions, okay? Now try to imagine another dimension that's perpendicular to all 3 of those. You can't do it. And even much less can you imagine a three-dimensional space orthogonal to another three-dimensional space. So this is all just a schematic diagram, if you will. We can still deal with these spaces. We can still do the linear algebra on the spaces just as we could in R2 or R3. So we do that. Now, this whole idea of any vector here being uniquely the sum of a vector in the row space and a vector in the null space is depicted just by, okay, here's a vector. There's some unique vector v row here and some unique vector vn here. Now, for this space, that's not important, but you can say the same thing over here. And in this case, the vector you want to look at is the b vector. Remember, that's the vector that has all the depths. Okay? That vector is almost certainly not in the column space of A. It's totally unlikely that you're going to get a vector with 6 components, or a vector that could have 6 components that really only has 3. I mean, that would give you 3 zeros, and we don't have 3 zeros in our B vector. So the point is then that our B vector ain't going to be in here, okay? At least not in the case that we're looking at. So you want to find the B vector that comes as close, you want to find the vector here that comes as close as possible to the B vector. Okay, so if this is, okay, first of all, for any vector x over here, AX is in here, right? Now you want to find the AX vector in here that's closest to this B vector. So what's the vector in here that's closest to the B vector? Well, it's just the projection of B onto this space. That's the B row. That's the unique vector here that can be added to a vector from the null space to get this vector. So you have a B row here and a Bn here. So here's your B row, unique vector in this space, Bn, unique vector in the null space. And that's where we want our x vector to map. Okay, so our equation is AX equals B. If AX equals B row, then X is the vector in Rn. Well, B row is the vector in Rn closest to B. Then, and you kind of have to accept that, but maybe in terms of these pictures, projections and stuff. It can be proven, but we're not going to go that far. We don't have time. Then, since B is uniquely equal to B row plus Bn, and B row is AX, then B is B row plus Bn, or AX plus Bn. And that means that AX plus Bn equals B, so that AX minus B is equal to negative BN, and you can just do the algebra. Let's set B equal to AX plus BN, do the algebra, and you see that AX minus B equals negative BN. Now the big thing about that is what? Bn is a vector in the null space. That's the only way you get this vector closest to the B vector. You're projecting along the null space. Bn is in the null space, and any scalar multiple of Bn is therefore in the null space, because any scalar multiple of a vector in a subspace is still in the subspace. So negative Bn is in the null space. Now what does it mean for negative Bn to be in the null space? It means that A transpose times this vector gives you 0. That's what a null space is. So this says that, okay, AX minus B is in the null space, and that means that A transpose times AX minus B equals 0. So we have this equation. The only thing we don't know in this equation is X. We know B, that's our column of the depths. We know the matrix A. We wrote that down a long time ago, and nobody had any trouble writing down that matrix because everybody kind of understands how we do this quadratic model. We don't understand all this yet, but we understand how to get a quadratic model for 3 points. Okay, so we take this equation and we just solve it for X. Now that's not very difficult, okay? How do we solve it? Well, let's use the distributive law. We get A transpose A times X, A transpose times B, and that minus that is 0, very straightforward. So that A transpose AX equals AB. Is that progress? Well, yeah, it is, because AB is just another vector in R6. And we can multiply it out. We know A and we know B. This is just going to be some column of 6 numbers. A transpose A. Well, A transpose has 3 rows and A has 3 columns, and it follows that A transpose A is a 3 by 3 matrix. So A transpose A has dimension n and is invertible. Now, I'm claiming it's invertible. Well, if the matrix reduces the way we said earlier, it is. So this is just a column. This is an invertible matrix, and now we can solve by multiplying this column by the inverse of the A transpose A matrix. And we can easily calculate the A transpose A matrix. Multiply A transpose by A. Might be messy if it's big, but you know, it's not difficult. Okay, alternatively, we could write just A transpose AX equals AB, and we would get from this a system of equations in A, B, and C, because of course X is the vector, column vector C, B, A. And then we could solve. So once we've got it to this, everything else is really just a matter of easy calculations, easy matrix calculations.